All right, so in this podcast, we're going to be discussing the most abundant element on our planet, which is carbon, and how we can use an isotope of carbon to check how long a bone has been dead for. So what we're going to start off with is the how carbon is made. So here we're going to have the Earth. So let's draw the Earth's crust. Nice there. There we go. Now, here's the atmosphere also. Let's just draw the atmosphere. Nice and atmospheric. So here's the atmosphere and here's the Earth. So 78% of the atmosphere is made up of nitrogen with 7 protons and 7 neutrons. So therefore its atomic mass is 14. Now, cosmic particles, which are simply just particles that come in from the sun into the atmosphere, they bump into things in the atmosphere and create lone neutrons. So we're going to call them N with a little 1. So every so often, one of these neutrons will bump into one of the N14s in the atmosphere and replaces one of the protons with itself. So essentially it changes it to 6 protons and 8 neutrons, changing it to a carbon atom. Changing it here, let's get rid of that there. Let's go back. N plus 1N equals a carbon 14 atom, which is the carbon 14. Carbon 14 is the 14 isotope and the most common isotope of carbon. So the excess proton that is bumped off of this carbon 14 here, it simply becomes one hydrogen ion, positive hydrogen ion. Alright, so now that we've talked about the process, how carbon-14 is made, let's backtrack a little bit here and talk about carbon. So carbon, by definition, has 6 protons. So let's write that, 6 protons and 6 neutrons. So there's the 6 protons and 6 neutrons, as you can see through the Bohr-Rutherford diagram right there. So the most common isotope of carbon is then therefore carbon-12. So let's write that there, carbon-12, which is the most common one in your body. However, there is a small amount of carbon-14 in your body that can combine with the oxygen to form carbon dioxide. So let's write that there, carbon dioxide, which mixes into your body. So once you exhale, this carbon dioxide mixes into the atmosphere. So let's draw a quick atmosphere up here quickly. Another atmosphere, an atmosphere. So this carbon dioxide then comes up into the atmosphere and makes carbon-14 again, as we explained before, because the carbon that is in the atmosphere is the carbon that you exhale and the carbon that is throughout the world. So let's say that a plant is going through photosynthesis and is taking carbon again. So let's draw a leaf here. Let's attempt to draw a leaf at least. Here's our, we'll call that a leaf. Anyway, so this leaf here is so this carbon-14 is gonna come down and is gonna be part of this leaf. Carbon-14 is now in the leaf. So now, in order for us to get the carbon-14 into our bodies, we're gonna have to eat the leaf. So we take this leaf and we shove it in our happy mouths, and now this person has carbon-14 in them, and that is how we get carbon-14 into our bodies. So now that we know how the carbon-14 is made and a little bit about carbon and how we get the carbon-14 into our bodies, let's talk about how it decays and how we can figure out how old a bone really is, which is what we're going for from the beginning. So the carbon-14 that is in your tissue gets frozen once we're dead and will decay at a certain rate. So let's write this rate down. The rate at which the carbon-14 is decayed is half gone in 5,730 years. So the rate is therefore, this is the half-life of the carbon-14 in your body. So what this means is that any carbon-14 atom will have a 50% chance of decaying into nitrogen-14 in that 5,730 years. So for example, let's say for some reason you go on a journey and you dig up a nice looking bone here. Let's draw a bone. This is our nice bone. So you dig up a bone and you say, hey, this bone has about half of the carbon-14 of everything that is alive today. So it would be safe to say, well, this bone is about 5,730 years old. So this is about 5,730 years old, give or take. And this is the rate at which carbon is decayed to figure out how old a bone really is. Alright, so now that we have talked a little bit about how carbon-14 is processed in our atmosphere and how we ingest carbon-14 in order for us to figure out our half-lives of the carbon that is in us to determine how old our specimens are, I'm just going to talk a little bit about limiting factors. So limiting factors of the carbon-14 dating. So there are some limiting factors, and here they are. First of all, I'm going to talk about the size of the archaeological sample. So the size of the specimen that you are using. So size. And for this, it is important that the larger samples are better. So large equals, that's not a very good G, good. So the larger samples are better. Now let me explain this. The larger samples are better because the purification and distillation remove some of the matter. So that means if you have a smaller sample, it's gonna take away some of the matter, which means it's gonna be even a smaller sample. Now there are some new techniques for working with these small samples, such as accelerated dating, except these ideas like accelerator dating are very expensive and still somewhat experimental, so they're not sure when they're going to actually be able to use things such as accelerator dating. Second of all, second limiting factor that I'm going to talk about here is how great care must be taken in collecting and packing these samples to avoid further contamination by more recent carbon. So let's just say contamination, or packing. Let's talk about packing actually. Packing. And in that, we're going to be talking about do not contaminate. And we're going to not want to contaminate these samples. So for each sample, we should use clean things to pack them in to avoid the cross-contamination between these samples. So the samples should be packaged in chemically neutral materials so that this avoids picking up new carbon-14 from the packaging. And the packaging should also be airtight to avoid contact with the atmospheric carbon-14 so it doesn't throw off your data when you go to actually test to see the half-life of the carbon in the specimen. So that's the second idea. So the third idea that we're going to talk about here, the third idea is since carbon-14 is not very accurate for the most recent deposits. So recent deposits. Recent. And in recent deposits, so little decay has occurred that the error factor, so the amount, the percentage that you have that is going to be an error for your experiment and for testing your specimen, is really large once the date obtained. So let's say someone died 2 days from today, or 2 days after, 2 days ago. So 2 days ago, someone passed away, and you took their bone. You obviously know that their bone has only been dead for 2 days, but you take their bone and you want to perform a radiocarbon dating. There is not enough half-life of the carbon-14 within these bones for you to even consider doing a carbon-14 dating trial. And because of this, you want to use older specimens. So older equals better. So older equals better. And this is just because how I explained, if a specimen is too young, you will not be able to determine the half-lives because the carbon-14 has not had enough time to actually go through its decaying process into nitrogen-14. So that's it for today. I hope you guys enjoyed, and I hope you learned a lot more about carbon-14, radiocarbon dating, and some of the limiting factors that occur in radiocarbon dating. So I just want to thank you for listening to my presentation, and I hope you learned.